Okay, something that we would like to look at, given f of x. So this is from section 3.3. I left out because I wanted to get that out of the way, and this is really we're going to start using that. Given f of x, to find the critical numbers, I will take a derivative, set it equal to 0, find where the derivative not exist, and come up with the critical numbers. I could do my testing, put the critical numbers there. So that's critical number 1, critical number 2, right? And I could do my testing and check where you have a maximum or a minimum. I have an alternative. If I find the critical numbers, and let's say that happens at A and B, I could take a second derivative and figure out where the second derivative does not exist. And I could do a testing and figure out where the second derivative is positive and where it's negative. If it's positive and if it's negative, kind of here. Let me just space those out a bit higher. There we go. So if I take, assuming this is the case, now here's the new deal, something that I didn't talk about. If A happened to fall in there, as long as it's not at the inflection point, isn't that a maximum? And if B happened to fall in there, isn't that a minimum? And the time you would use this, if you could take a derivative and another derivative and get rid of one of the variables, this will be easy to do. For example, polynomials. Every time you take a derivative, you lose a power, a term. And I'll point those out as we do problems, and I'll show you how to do it both ways. I did it the long way so that if you're ever confused, this works all the time. The only time this will not be beneficial, if this A happened to be at the inflection point, then you have to go back and do this. But I'll show you how that works. So that's what this is talking about. Reading the actual test is kind of confusing. If you have a derivative that's always positive, that means a second derivative is positive, the graph is concaving up. If you put the value in, and that would mean it is a minimum. And if you have a second derivative that is negative, that means the graph is concaving down. And that value, if it happened to be in there, that is a maximum. And they say the test failed if it happened to be at the inflection point, which is an exception. So let's start this section. This section talks about, this is page 205, talks about business and economics applications. We're going to break this into 2 lectures. The first lecture, we're going to talk about, what do you call them? Maximizing, minimizing, the usual, traditional. One thing from now on we're going to figure out to study the effect of production level on cost. One method economists use is the average cost function. Take the cost function and divide it by the number of units. And let me elaborate what that means. Instead of people coming to you and saying, you know what, the production of iPhone was $3 billion. Okay, you say, okay, well, can you tell me what the average cost is? You're taking the $3 billion and you're dividing that by how many units were produced. Let's say they produced 1 million or 10 million or 100 million, you know what I mean? So if you say the total cost was $1,000, okay, the total cost for what? To make 200 teddy bears. Then the average cost, the cost per 1 unit is roughly $5. But we're not putting numbers, we're using the actual function, and we figure out the change of rate of that and figure out the maximum. This helps a lot. So from now on, from this moment on, anywhere you see the word average cost, you're going to take the cost function divided by x. Just like if we want to figure out revenue, that's always x, the number of units, times the price per unit. So how many units did you sell times each price gives you the total. That's also something that you need to be using all throughout. Well, let's see how this goes. So the first half of this section is to really get you into this maximum minimum idea and get things out of the way. In 1 through 4, find the number of units that will maximize revenue. Okay, let's see. Maximize. Maximum or minimum, I know how that works. That works at a derivative. Isn't that, what is that? 96x minus 0.06x squared. So I need the critical numbers. I need to know, where does r prime equal 0? Where does r prime not exist? Well, if it's a polynomial, this could never happen. If I set this equal to 0, wouldn't that be x into 96 minus 0.06 x equals 0? That means x equals 0, or x equal, and I have a calculator, I'll get that out, make use of it, 96 divided by 0.06, 1600. Now, this is the deal. This blue part I could avoid. Let me show you. I could stop here. I really don't need the second derivative. I could say this is r prime and this is r. And I could say 0. Well, 0 always is useless. And I have 1600. It doesn't make sense to talk about negative units. So I could pick a point to the left of 1600. Say 1. If I put a 1 right there, that's positive. You just want to know if it's positive or negative. If I put a 1 right there, 96 minus 0.06 is positive. So the revenue is going up. And if I pick a number to the right of 1600, say 1700, if I take 96, and I'm putting it right there, since I'm using a calculator. If I take 96 times 1700 minus 0.06 times 1700 squared, I'll get negative. That's all I care about. So doesn't this automatically tell me that we have a maximum revenue? They're asking only for the number of units when 1600 units. Actually, let's say at 1600 units. Now let me show you a trick. I could have avoided the blue, but I still have to figure this out. I still need to get the critical numbers. But the testing, I could have taken a second derivative, and look how that will benefit me. Isn't the second derivative 96 minus 0.12x? Where does that equal 0? That equals 0 only when x equal, I have a calculator. What is 96 divided by 0.1? Oops. 12. 11.5. Something's not right. 0.12. If I take 96 divided by 0.12, 800. Okay, that's more like it. 800. Watch what happens. Here, I'm only testing one point, the point to the left and the point to the right. Remember, 1600 is the only point that I care about. So I only care about this part. If I pick 1, I could tell this is positive. This is concaving up. If I pick 1,000, 120, 96 minus 120 is negative. This is concaving down. Do you see that 1600 is right there? Isn't that a maximum? So instead of having 2 values, you get only 1. You really don't have to do this at all. The first derivative test will do. You don't have to do the second. Okay, and I'm going to show that anyways on almost every problem, page 213. Here's another derivative function, number 4. If I take the derivative, bring the power down, subtract 1 from the power. Divided by 3, that's a 10. That's 20 over the cube root of x minus 2. R prime is 20 minus the cube root of x over the cube root of x. So, where does r prime equal 0? Where does r prime not exist? Well, r prime not exist if the denominator equals 0. That's when x equals 0. That doesn't help us much. And r prime equals 0 if the top equals 0. 20 minus cube root of x equals 0. Right? That's when 20 equal the cube root of x. And if you cube both sides, you'll get x to be, oh boy, what's 20 cubed? 20 raised to the 3rd power, 8,000. So, in this case, I could go in and say, let me do my testing, or let me show you really quick. I got the critical numbers. So instead of doing this part, all of this part, instead of you going in and saying, look, there's r prime, there is 0, there's 800. We're not going to pick negative. Let's pick 1. This is positive. 20 minus 1 is positive. This function is increasing. And if I pick a point to the right of 800, say 1,000. Cube root of 1,000. I'm sorry, not the 1,000. 8,000. If I put in a million, that's 10 to the 6. So this is going to be positive, but the top will be negative. Positive over a negative is a negative. You have a maximum right there. Another way of doing this, observe this. If I take a second derivative, right, 3 divides, if I take a second derivative, remember, that's 20, bring the power down, subtract 1 from the power. And do you see this becomes a 0? R double prime is negative 20 over the cube root of x to the 4th. Where does r double prime equal 0? Where does r double prime not exist? Well, a fraction equals 0 if the top equals 0. That's not possible. It does not exist at 0. And notice here, I only have 0. I don't worry about negative. There's r double prime and there's r. If I pick a point to the right, say 1. If I put a 1 there, isn't that always negative? If it's negative, isn't it concaving down? And isn't 8,000 right there? That automatically tells you you have a maximum at x equal 8,000 units. Now, which of those do you want to use? It's up to you. I am going to stick with using this and this. Just make sure that, and I'm not going to ask you to do one or either on the test. It's up to you. If you want to stick with the first derivative test, you're welcome to do that. I want to look at the next problem, problem number 6. And here they're saying, find the number of units that minimize, smallest, lowest, least, that's a minimum. Largest, biggest, maximum, I don't know, any other word that means high, that's maximum. For the average cost, so the average cost is the cost function divided by x. You gotta remember that. That is 2x squared plus 348x plus 7200 divided by x. The cost function is, you split that up, and I'm going to show you that because some of us are messing those up. That is 2x squared over x plus 348x over x plus 7200 over x. The cost function is actually 2x plus 348 plus 7200x to the negative 1. That's the function I want to maximize or minimize. How do you do that? Easy. Take a derivative. That's a 2, that's a 0. Bring the power down, subtract 1 from the power. Right? Now, if I was you, I'm going to find the critical numbers. I'm going to do the cleaning here, and there's no way around that. That's 2 minus 7200 divided by x squared. That is 2x squared minus 7200 divided by x squared. So my critical numbers would be where does the derivative equal 0? Where does the derivative not exist? Well, this is when x equals 0. That's always the case. That's useless. This one is when 2x squared equals 7200, x squared equals 3600, and x would equal 60. Look at that. I didn't even need a calculator. I could have used my calculator. It's really plus or minus, but we're going to ignore the minus. So here, I could do negative 60 as 0 and 60. I really don't worry about that. So I could do c prime, but watch. If I go for the second derivative, right away, isn't the second derivative, right there, messed it up kind of, isn't the second derivative 0, bring the power down, 144,000 x to the negative 3. So isn't the second derivative 144,000 over x cubed? The only point of inflection or possible is a 0. I don't worry about negative. Do you see that this is always positive if you pick any value in there? And isn't 60 right there? Automatically that makes it a minimum cost, or here, minimum average cost when the units are 60, when you produce 60 units. You want to do the testing here, you're welcome to do that. We know how to do that, right? Pick a point right there, test it in there, pick a point right there, and obviously it's going to look like this. So the second derivative test could benefit you if you're dealing with certain functions. Again, you don't have to use it. Number 8, if I find the average cost, that's the cost function divided by x, divide this by x, this by x, this by x. That becomes 0.02x squared plus 55x. Plus, I'm going to write this as 1380x to the negative 1. Take a derivative. 0.04x plus 55 minus 1380x to the negative 2. And if I figure this, let me check really quick. This is 0.04 x plus 55 minus 1380 over x squared. Okay, so this is 0.04 x cubed plus 55x minus 1380 over x squared. It turns out where the c prime equals 0, when x equals 5, they use a graphing calculator to do that. You're not responsible to know that. I thought all of these could be done by hand. The homework you're going to do will be for sure, you'll be able to do it by hand. And it turns out, if you really look at this, this is negative to the left. Again, I'm not interested in this problem because how are you going to get the 5? But if you were able to, this is c prime, so we have a minimum average cost when x is 5 units. So instead of erasing this, I already did the work. Let me just leave it there. That's not a problem. So nothing like this on an exam because it requires a graphing calculator. We're not using a graphing calculator. And the next set of problems, I have 2 of them. Actually, I want to do one of those, 10 or 12, and number 16. All right. Let's do 10. The next is 9 to 12. Find the price that will maximize profit. This is the demand function. This is the cost function. And how do you find the profit function? We know that the profit is revenue minus cost. And the profit is going to be revenue. What's revenue? It's the demand times x minus the cost, which is x times 70 minus 0.01x minus 8,000 plus 50x plus 0.03x squared. So the profit is really negative 0.01x squared plus 70x minus 8,000 minus 50x minus 0.03x squared. And the profit would be negative 0.04x squared plus 20x minus 8,000. That's the profit function. So what do we need to do here? We need find the price that will maximize the profit for demand and cost function, where P is the price, X is the number of units. And see, okay, well, we take a derivative, no big secret. That's negative 0.08x plus 20. And where does that equal 0 to find the critical numbers? That's when X equal negative 20 divided by negative 0.08, or divided by 0.08, I'm getting that to be 250. Now, this is my critical number. Observe how useful a second derivative would be. Isn't that negative 0.08? If I want to do my testing, you say, wait a minute, but the second derivative can never equal 0. That's actually a good thing. Why is that? Because no matter which point I pick, let's say I pick 5, what's the second derivative? Isn't it always negative? If the second derivative is negative, isn't that concaving down? Isn't the critical number in there? Automatically, that makes it a maximum profit when X is 250 units. You will make the most profit when your units, when you sell 250 units. So keep in mind, this takes a lot of things into account. You might be thinking, but the more you sell, the more you make. Well, if instead of opening 12 hours, say I have a shop and I sell 1,000 pieces, if I open for 24 hours and I only sell an extra 20 pieces, the utilities, the employees, that'll cost a lot more. So it's not always the more the better. It depends. And I want to do that one as well. So maximizing profit, a commodity has a demand function of and a total cost where X is the number of units. What price will yield the maximum profit? So the profit function is the revenue minus the cost. That is x times p minus c. The profit function is the revenue. The revenue is 100 minus 0.5x times x minus the cost function. Make sure to use parentheses around that. So the profit is negative 0.5x squared plus 100x minus 50x minus 37.5, and the profit function will be 0.5x squared plus 50x minus 37.5, and you follow the same trend as above. You take a derivative of the profit, that is 1x plus 50. Okay, that's simple. Set that equal to 0. Well, something's not right. Let me check what's not right. Oh, no, that was right. That was 100. That was a negative. That was 50. There's a mistake. This was a negative. So I'm getting x to be 50. And again, instead of doing the test there, just observe. If I take a second derivative, so this is the critical number, isn't that negative 1? And think about it. If a second derivative, no matter what you pick, it's always negative, then the function is concaving down. That makes this a maximum profit when x is 50. What do they want? What price will yield a maximum profit? Price would be, there's the price, 100 minus 0.5 times 50, that's 25. So that is $75 per unit. Part B. And the total cost, in part B. When the profit is maximized, what is the average cost per unit? The average cost per unit is, what did we find it to be? Take the cost, 50x plus 37.5 divided by x. Evaluate it at x equal 50. What is that? Well, I have a calculator. Parentheses, 50 times 50, which is x, minus 30 plus 37. Okay, third time will be a charm. 0.5 divided by 50. $50.75 is the average cost per unit, the average. One more to go, and point of diminishing return is extremely important. And here we're doing what? It says, find the amount S spending on advertisement in thousands of dollars that maximize the profit in thousands of dollars, then find the point of diminishing return. So you want to maximize advertisement, right? Maximize the profit, and the profit is given by this function. Well, we not find a maximum of anything, we take a derivative. Where does that equal 0? You want the critical numbers. So take s into negative 0.3 plus s plus 12 equals 0. Either s equals 0 or s equal 12 divided by 0.3. 12 divided by 0.3, that is 40. And if I do my testing, now, since I'm going to find the point of diminishing return, might as well, since I'm going to take a second derivative. If I take a second derivative of this, isn't that negative 0.6s plus 12? Where does that equal 0? So I have to find this point anyways. That's when S equal 12 divided by 0.6. Is that 20? And notice, instead of doing 2 tests, I only have to do 1. And I'll really nail 2 answers with 1 attempt. There's 20. There's P double prime, there's P. If I pick 1, negative 0.6 plus 12 is positive. If I pick 100, negative 60 plus 12 is negative. So we have the point of diminishing return is really when x equal 20. And if I take 40, isn't 40 to the right of 20? We have a maximum when x is 40. I keep on saying x. When s is 40. Sorry about that. I'm so stuck on x. When s is 20 here. You could do the testing there, but this is a lot more efficient. And there's your homework. 3.5, you're going to do numbers 1 through 17 odd, and you're going to skip number 30.